Hello and welcome. So last time we talked about verifying solutions to a differential equation, and the big question you all asked was, well, can you actually find the solutions without them just being given to you? And the answer is maybe. So one of the things is that this method does not work for all differential equations. This method will only work for a certain type of differential equation called a separable differential equation. And so that's what we'll be focused on. That's the only strategy that you need to know for this course. As I said last class, in BC, you learn a couple extra strategies. And in other calculus classes, if you move beyond, you learn quite a bit more. In fact, there's an entire course you could take probably called Differential Equations if you get to college. That focuses on all the different strategies. I took that course. I don't remember it. So if you ask me, I can point you to the textbook that's in my room, and you could take a glance at it, but I'm very bad at remembering those things. Anyways, so here we go. Here's our first problem. We want to solve the differential equation dy over dx equals x squared over y squared. Or in other words, y prime equals x squared over y squared. But I wrote it out this way, and you'll see why in a little bit to make it a little more clear. And then after we find that solution, we're going to find the very specific solution that satisfies this initial condition. So we need to have it so that way when x is 0, y is 2. So you'll remember from the last video, you can find sometimes the solutions are a function family. And so that's what we'll be doing first is like, what's the function family? And then ultimately, what is the actual specific solution that goes through here. All right, so let's do number one first. We're going to solve number one to start out with. So I'm going to start with the original equation, dy over dx is equal to x squared over y squared. Okay. So goal number one here is to get all the things with x's on one side of the equation and everything that has y's on the other side of the equation. Specifically, I want them to look like blah dy on one side and a blah dx on the other side. I don't want to be dividing by dy. I do not want to be dividing by dx. I want to multiply because that's going to start to look like the part that shows up after an integral. And if we can do that, then we can integrate both sides. That's the whole idea. So the first thing we're going to do is we are going to multiply both sides by dx. That's going to be my first step here. So that's going to leave us with dy equals x squared over y squared dx. And now I'm going to go ahead and move the y squared over by multiplying by y squared on both sides. So now that gives me y squared dy is equal to x squared dx. So I have all my x's on the right side, all my y's on the left side. And like I said, this now looks like sort of the parts that show up after an integral symbol. And so oftentimes we would differentiate both sides of an equation to sort of help us solve. Here today we're going to integrate both sides with respect to the variables that it says there. So on the left side here, it's going to be 1/3 y cubed. And on the right side, it's going to be 1/3 x cubed. Great. So here's the thing. These were both indefinite integrals. So we're not talking about a specific area. Instead, we're talking about a function that represents that area. And so because of that, we're thinking about a function family. So I could write a plus a constant here and plus a different constant over there, but then I could actually subtract this constant over or that one over to sort of make it so that way there's only one constant. So that's the long way of saying basically you don't have to worry about writing plus c on both sides. You can just write it on one side, and that actually covers if there were two different Great. So now at this point, we are going to solve for y. Now, this is not always possible. It's not always possible to be able to solve for y. Sometimes it's not, and you need to be able to recognize that. In this case, we totally can solve for y, since it just shows up one time, and I know all the undo steps here. So first thing we're going to do is multiply both sides by 3. So that's going to get us y cubed equals 3 times a third is just 1. But then now that turns my original constant into a 3c, which is still a constant. So like you could get fancy and be like, oh, I'm just going to go ahead and call that k or something like that. But you don't have to. You could write it this way. I'm going to keep it this way. The final undo step is to take the cube root of both sides, which gives us y equals the cube root of x cubed plus 3c. And there you have it. That is our final answer to question number 1. So this is a solution. All functions of this family here are a solution to this differential equation. And you could check it out by taking the derivative of this thing, plugging it in for dy over dx, and then plugging this thing in for y here, and verifying that it works. I will not do that, but you could do that, is what I was saying. That's what we've been doing. All right, so now let's talk about the second thing here. We want to find the specific solution that will go through the point 0, 2. So how do we do that? Well, it's not very different than what we have been doing in terms of finding specific solutions. If we know that the y value must be 2, then starting with this equation down here, we have that 2 is equal to the cube root of, instead of x cubed, we'll have 0 cubed plus 3c. And now I'm going to solve. So we'll take, let's see here. Oh, let's simplify before I start solving. So the cube root of 3c. So I'll cube both sides to get me 8 equals 3c. At this point, I could solve for c, but I noticed that really what I'm looking to do is replace the 3c with something here. And so since I've solved for 3c, then I can just replace that here. So that gives me my final answer here, which is that y equals the cube root of x cubed plus 8 as my final solution. And there you have it. So to recap, first thing to do is get your x's and y's on different sides, and you want it to be times dy and times dx. You do not want divided by, because when you go to integrate, you want the dy dx to be in your numerator. So it's okay if you had y squared in the denominator or x squared in the denominator. If that ends up happening, that's fine, but you don't want the dx in the denominator. So integrate both sides. Remember, you only need to have plus c on one side. I usually throw it on the side that has the x in it. And then try to solve for y if possible. Remember, it is not always possible to isolate y, in which case you can just sort of stop right where you find sort of this step here. And then if they give you more info, you can find the more specific function or equation that is a solution for this. All right, that does it. So we'll do more practice on this in class, and we'll sort of see how we can use this to help us model some populations. So if you could please now take the survey and answer a couple questions, that would be great. Thank you.